So as we begin Module 4, we'll be relating back to Chapter 3 in our textbook. We'll be looking at 1D steady-state conduction. Particularly, we're treating situations in which heat transfer by diffusion under 1D and steady-state conditions. So we'll break this module down into two different sections. This right here is the first section, Module 4.1. We're going to look at the methodology of conduction analysis, particular our plane wall and composite wall. And then for Module 4.2, we'll continue on with our radial systems, the tube wall and spherical wall. Relating back to your readings in the textbook, this is going to cover sections 1 through 4 in the text, and I would advise you also to please read ahead in the textbook before next module, Module 5, and continue on reading past section 4 for Chapter 3. So for this first section here, Module 4.1, we're going to take a look at conduction analysis for 1D steady state conduction with a plane wall. We'll look at geometries, equations related to the plane wall, temperature distribution, thermal resistance, take a look at applications for the composite wall and how we relate equations for that, go through some more practical applications, and do some problem solving where I go through my hand solutions. So as I mentioned, we're going to begin Chapter 3 in our textbook with this module here, particularly looking at sections 3.1 through 3.4. This is when we're dealing with this 1D steady-state conduction. Now we're dealing with it now at first without any thermal energy generation. As we continue on in this course and move forward, we will introduce some thermal generation as well and see how things vary with that. But for this chapter in this section right here, we're dealing with it without any thermal energy generation. So first, let's talk about discussing the methodology of conduction analysis. How do we approach these types of problems we're dealing with this? Well, we have a couple different things that we've seen before as we've been working through example problems. The first thing that we want to do is to specify the appropriate form of the heat equation. How do we do this? Well, this is why it's important to have that setup page in our problems. When we read through these problem statements, we really want to understand everything that they've given us and what they're asking us to solve for. And with that information, along with any assumptions that we can make based upon the information they give us, we can then go ahead and look through our governing equations in order to specify this appropriate form of the heat equation for our particular problem. From there, what we want to do once we have that information is to go ahead and solve for our temperature distribution, and then from there we can apply Fourier's law in order to determine our heat flux. So as I mentioned in this module here, what we're going to be doing is looking at the simplest case. And the simplest case being that we're only dealing with one dimension and a steady state with no thermal energy generation. So this really does, all these things together really simplifies down our solution. First, we're going to take a look at some common geometries. And for this first section here, we'll just concentrate on the first one for Module 4.1 and look at the plane wall. So this is going to be described in rectangular x-coordinate. The area perpendicular to the direction of heat transfer is constant and independent of x. So that's why we're saying this is just 1D. It's a plane wall, but we're only concerned in going that 1D direction for that there. Now, as we move on to Module 4.2, then we'll start looking at these two geometries here, where we're dealing with a tube wall, which has radial conduction through that tube wall. It's not 1D, though, one direction through it. And then spherical shell, where we have radial conduction through the shell wall. So these we'll get to when we look at section 4.2 within this module. So let's take a look at the plane wall. In this example here, we're going to consider a plane wall with two fluids, each of different temperatures, acting on either side of a wall. So we can see we have this diagram over here where we can see off to the left-hand side of the wall, we have this hot fluid temperature right here with a value given to us as T infinity comma 1. And we have an H value of H1, where H is the convection heat transfer coefficient right there. And now on the other side of the wall, over on the right side, we have another fluid here, a cold fluid right here. So these are the two different fluid temperatures that they're talking about in the problem statement right there. So with this cold fluid, again, we have the temperature of the fluid right here, T infinity comma 2, and we have our H value again, the convection heat transfer coefficient right here of H2 right there, acting on the right side of the wall. Now we can see in the wall itself, it does have a surface temperature on the left side right here. So the surface temperature of the wall here is TS1, and on the right side over here, we have another surface over here, surface 2, which we call the temperature here, TS2. Now, the way this wall is defined, we can see here we have our 0 right here, and then we're going to move in the x direction as we go to the right here. So as we move into the x direction right here, we get to some certain distance over here where x is equal to the thickness of the wall, which is our L value right here. So oftentimes we'd be interested in what is the temperature at some distance in this x direction within our wall here. So this is our temperature distribution. So temperature distribution in a wall can be determined by solving a heat equation with the proper boundary conditions. That's something that's important here, is that we are dealing and looking at the proper boundary conditions. Whether it's given in the problem statement or we can infer those right from the diagram, those need to be established in order to use this here. So this is our general heat equation right here for the plane wall, and this comes from equation 3.1 back in our textbook here. So we have ddx of K, which K is our thermal conductivity, times dt dx, the change in our temperature with respect to that distance x, and this is equal to 0. So this right here is our general form of the heat equation from equation 3.1 in our textbook. Now there are some implications down here that we can see. The implication is that our heat flux, our Qx double dot, is going to be independent of that distance x. No matter where you are in the wall, your heat flux is going to be independent of that location. Same as our heat rate, our Q of x right here, and we can see there's our Q of x right here. This is also going to be independent of this direction x as well. So now we get into these boundary conditions. We said we have to have the proper boundary conditions in order to utilize this heat equation right here. Well, what are our boundary conditions right here? Well, you can take a look and we can look at our diagram right here, and what we can say is at x equals 0. Well, if we're at x is equal to 0, that means we're on this surface of our wall right here. So if x equals to 0, our temperature when x is equal to 0 is equal to this TS1, which is our surface temperature at that wall. And we can also see the other boundary condition, think of the boundary as bounding this wall, is when x is equal to L. So if we plug x equal to L into this right here, our T of L, so when our distance x is at this distance over here of L, we're at this surface of our wall right here, the outer surface over here on the right hand side where it's exposed to the cold fluid, and then our temperature there is equal to our Ts comma 2, which is given to us right in that diagram. So those are our boundary conditions based upon the information given to us in the diagram there. So now the question is, what is the temperature distribution for a special case where our K value is constant, where again K is our thermal conductivity? Now just a side note, one thing I like to do is to reference back as I'm looking at these equations. I know in this course there's a lot of different equations, a lot of different subscripts, and you're not always going to have them memorized. So rewriting them out for yourself as a little note here when you're dealing with the problems, when you have a lot of these governing equations, you want to make sure, okay, specifically for this problem, what is my T1? What is my T2? What is my TS? What is that? So I would highly suggest that you guys do the same type of thing and write out a little note to yourself and to the grader or anybody else following through your work of what each of your variables are. Now, if you have any questions to what these variables are, the textbook has a great booklet in the beginning of it. There's a couple pages where it goes through all the symbols. I've also provided a PDF on Blackboard for you as well, a 10-page PDF relating all the different symbols and governing and key equations for this course related to our specific textbook. So that's just a side note as far as dealing with variables and symbols. Make a note to yourself. Please reference back to the beginning of the textbook and the attached PDF on Blackboard for your governing equations and symbols. So that being said, we come down here for our temperature distribution for a constant K value or a constant thermal conductivity. We have this relationship given to us by equation 3.3 in our textbook here, where T of x, our temperature at some position x along the way from to x equals 0 all the way up to x is equal to L for our particular case here, is equal to, for our problem here, our TS1, which is our surface temperature here where x is equal to 0, plus now we have in parentheses here our TS2 minus TS1, which is our surface temperature when x is equal to L minus our surface temperature when x is equal to 0 right there, times this ratio of x, which is our position where we're interested in from our initial start point 0, divided by L, which is the total thickness of our wall there. So this is equation 3.3 in our text. So referencing back to our textbook here, we have some governing equations we can utilize for heat flux and heat rate as well. So we can see here that our heat flux is equal to our negative K, where K is our thermal conductivity, times our change in temperature with distance, our dx, so dt dx. And this is equal to K, again, our thermal conductivity, divided by the total length times the difference in those surface temperatures. So TS1 for our particular case in our diagram we just looked at there is our left surface temperature, and our TS2 is our right surface temperature. So this right here, our K over L times the temperature difference is equal to this negative K times dt dx. So we're simply putting in there that change in temperature with respect to that distance x right there. Now for our heat rate, we have a similar equation down here. Difference is now we have area is going to be now involved here. So if we go looking again back to the difference between our heat rate and our heat flux, that is that area there. So our heat rate in the x direction is equal to our negative K value, our thermal conductivity, times now that area, times now the change in temperature with respect to distance right there, dt dx. So when we say what is that change in temperature, what is that distance right there? So the change in temperature right here is TS1, the surface temperature 1 minus surface temperature 2 right there, times now Ka, because we have the A term in there, divided by the total thickness or length there, L. Now these relate back to, for our heat flux, equation 3.5 in our textbook, and for our heat rate, equation 3.4 in our textbook. So going forward with solving these problems, the next thing I want to discuss here are thermal resistances and thermal circuits. Now thermal circuits are going to be great, and it's really interesting how we can line these up with that initial diagram that we just saw in the previous slide to create these thermal circuits. But going back to thermal resistance right here, our thermal resistance, or R sub T, is in general form our delta T, our change in temperature, over our Q value there. And again, we want to recall what are our symbols right here. What is our Q? So our Q is our heat transfer rate, so units of watts right here. So that's another thing that we really want to do is we're utilizing all these formulas here and all these governing equations is pay attention to unit analysis. One, look at the symbols, reference back to the symbol table in your textbook, go to the PDF that I provided on Blackboard for these symbols, and understand not only what the variables mean, how they relate to your problem, but also what units are used. And using unit analysis will really be helpful in solving some of these problems and double checking your work. So now this thermal resistance is going to be different for conduction versus convection, and are we dealing with a plane wall or different geometry and shapes there? So let's just consider, we're continuing on the plane wall right here. If we're talking about conduction in a plane wall, our thermal resistance, or R sub T here, and now you notice my indices here, I've also put comma conduction. This is important as well to come up with our own indices to really clearly label what it is we're solving for. So when we plug back into other equations, as we continue on with our solution to a problem, we understand exactly what we have. So we call this here our thermal resistance for conduction in a plane wall, or R sub T comma conduction here, is equal to, in this case here, this comes from equation 3.6 in our textbook, our L, which is the thickness or the length of that wall right there, divided by Ka, our thermal conductivity, times that area. So this is for conduction in a plane wall. Well, what if we have convection? So convection right here, we have this following equation here. You can see, change my indice again here now, R sub T for thermal resistance, but now I'm dealing with convection. So I put comma CONV for convection right there, and that's given by this relationship shown by 3.9 in our textbook here, where we have 1 over HA. So again, these are 3.6 and 3.9 from our textbook for thermal resistances for both conduction and convection when dealing with a plane wall. So what we're going to do now is utilize this relationship here for conduction and convection for these plane wall for thermal resistances here in order to create what we're calling a thermal circuit down here. So this is an example of what a thermal circuit would be right here. So this is a thermal circuit for a plane wall with these adjoining fluids. So this goes back to that same diagram we saw before. Now before I get into the details of this, I'm going to rearrange this and put this thermal circuit directly under the initial diagram that we just saw. And I think this is very helpful when we're solving, to get that visualization, say, okay, here's a point here, here's a point here. Okay, I need to find the equation for each section along the way. And from that there, we can then use, we can ask ourselves, okay, from this point to this point here, from our surrounding fluid temperature to our surface temperature, what do we have going on there? Well, if we look at this here, we can say, okay, well, that's convection going on there. I'm going to use my convection term from 3.9. Let's say from the surface 1 to surface 2, when we're going through the wall itself, what's going on there? Well, I can say, okay, that's going to be actually conduction as I'm going through the plane wall right there. That goes back to a relationship 3.6. I have this L over Ka. That's where I come up with that there for conduction. Then if I go from the other side right here, the surface of the wall there and our surrounding fluid temperature over here, well, that's convection again that we have occurring right there as we're going through a fluid. So therefore, I have my convection equation here, and I write that down there. Now again, the thing to note with these two convections is pay attention to your H value right there. This is for your condition 1 with that fluid over there on the left-hand side of the wall, and this is for your fluid on the right-hand side of the wall. Same thing with our temperatures. Our indices become very important right here to letting us know where we are. So from that information there, what we can do is we can say, well, our total thermal resistance is going to be the sum of all these internal thermal resistances right here. So I can add up 1 over H1A plus L over Ka plus 1 over H2A, where this is my convection on the left side, conduction through the wall, convection on the right side. Now this comes, if we go back to our textbook equation 3.12, and similarly we can solve for our Q sub x here, our heat rate. Our heat rate is given by equation 3.11, where we have the temperature difference of the fluids on either side of the wall divided by that total thermal resistance, and that's how we can get heat flux out. So this is why it's important to draw our thermal circuit in order to calculate our total thermal resistance, in order to go back to plug in to calculate our heat rate. So this is where I was saying, doing unit analysis out, paying attention to your units, really pay attention, start with your general form of the equation, plug them in, and pay attention along the way where you clearly understand what your variable names are and your indices and how they relate to your problem. All becomes very, very important. So what I've done here is we're going to recap what we just talked about in the last slide, but now give a visual of how we can actually draw this thermal circuit out. And this, again, is very beneficial, helps you keep track of things. So I look over here and I say, okay, what's going on in my diagram? Well, I have this hot fluid over here. I know the temperature right here. I have my H1 value right there. And then over here on the other side, I have my cold fluid over here. I have the temperature of that fluid, and I have my H value there as well. So I can see, well, I've got a temperature right here at this point. I've got a temperature right here at this point. Got a temperature over here and a temperature over here. So I have 4 nodes along the way that I can use to create my thermal circuit. So this is for temperature distribution. So you think of this thermal circuit for temperature distribution. So we come over here and we're calculating our thermal resistance. This is a thermal circuit here. So I draw from this node here, I write a node down here. From this node here at the surface, I draw a node down here. From this surface here, I write another node there. And from this over here, draw this other node right out right there. So now I've got all 4 of those relating to those 4 temperatures related back to this initial diagram here. I can begin to draw my thermal circuit. So this is where I ask myself, what is occurring between these 2 points, or these 2 nodes right there? Well, I have my my fluid temperature over here for my hot fluid, and I know that's T infinity, my H1 value right there. And to go from here to here, this is convection. So I can go back up to my convection equation, 3.9 from my textbook right here, and write that in right there with the appropriate variables. This is where having your indices correct is very important. So this is from T infinity 1 to TS1. T infinity 1 to TS1 is my 2 temperatures right there that I write out. And the equation for convection down here is 1 over HA, where H is 1, is my H value there. So then I move on to the next. Now I'm going from TS1 to TS2 on my diagram here, the 2 surfaces of this wall. Well, how do we transfer heat through a surface through the wall itself? Well, that's going to be our conduction equation, equation 3.6. So this is my R sub T, conduction, is equal to my L over Ka. I plug that right in there, L over Ka. I don't have any indices here. This is my L distance right here. That is the total thickness of the wall, starting from my surface temperature here, where x is equal to 0, all the way up to x is equal to L over there. So then that goes from TS1 to TS2, from those 2 surface temperatures right there and there. And then I go from my surface temperature TS2 to my surrounding cooler fluid over here, and I say, okay, well, what's going on there? Well, that is, again, going to be convection right there through that fluid right there. But now I have TS2 and T infinity 2 that are my 2 temperatures right there. And I have my value right here of H2 for my cold fluid right there. So that's where I come up with this relationship here of 1 over H2A. So that is a great way to draw out a thermal circuit. I really do like to do that. Even if it takes an extra page and a little bit extra time to redraw out your initial diagram, line everything up, and you can ask yourself those questions. What's going on from here to here? From here to here? Especially as we get into some composite structures where there's more things going on than just one solid material in the wall. We have different H values. We have different things that we need to plug in there, different K values if we're dealing with the actual conduction value as well. You know, is there an air pocket in the wall? Are we talking about a double insulated window? All those type of things. As this diagram becomes more complicated, your circuits become more complicated, but if you can line them up right underneath each other, it makes your life a little bit easier in creating this thermal circuit. So from there, that's where we came up with these two equations we discussed on the last slide, 3.11 and 3.12, where 3.12 is that total thermal resistance right here, where we add up all these parts right here of the thermal resistance that we calculated from each portion along the way between those nodes, add those together right there, and that's your 3.12 equation, whereas 3.11 is saying, okay, that value that we just got right there from 3.12, we're going to plug in on the denominator here in order to calculate our heat rate right here with the temperature difference between the two outside temperatures right there, my T infinity 1 and my T infinity 2, between my hot and my cold fluid, and that's temperature difference we're concerned with there in order to calculate this heat rate. So next, let's take a look at thermal resistance for unit surface area here. Now, if we take a look and note here, the variable name is different now. We now have an R sub T double prime. So this is our thermal resistance for this unit surface area. And we look over here at the actual formula for this, there's no longer an A in this term here, and that's because it's per surface area. So we also notice the same thing over here, and we're dealing with convection. We have an R sub T double prime over here for convection of 1 over H, and again, that A is no longer there. Now, if we take a look, if we're going from our R sub T to our R sub T double prime, which again, our R sub T double prime is for our unit surface area, we again notice when we have this here in our units right here, there's that meter squared, noting that it's per surface unit area. So that's going to be the main difference in the equations we've seen at the previous slide as compared to our equations here. Now, continuing on, if we're looking at radiation resistance, we have the equation down here. So we have our R sub T for our thermal resistance for radiation right here. So again, these indices become important. We really want to pay attention and make sure when we're writing these out, we include, is it conduction, is it convection, is it radiation? So if we're dealing with radiation for our resistance down here, we have this relationship here where we have 1 over our H sub R times A. Where if we come over here, I've again made a little table off to the side where I've noted what each of our variables are here. So H sub R is the radiation heat transfer coefficient. So that's our H sub R that we put in there. And this again, you notice there is not a double prime. This is just our thermal resistance here. So we do have this area term in there. If we want to do this for the thermal resistance for radiation, so our radiation resistance here for a unit surface area, we now have this relationship here. We have our R sub T double prime, denoting that it's per unit surface area here. And this is equal to 1 over our HR again, where that HR is the radiation heat transfer coefficient, what we know over here. And now again, we notice here per unit surface area, we no longer have this A term in our relationship there. Now this leads into the question now for HR, our radiation heat transfer coefficient, what is our relationship there? Well, we can go back to chapter 1 in our textbook here and we can see equation 1.9. We have this relationship shown here. We have our epsilon to sigma times our T sub S plus T surround times now our Ts squared plus our T surround squared there, where our T sub S, if we look over here, is our surface temperature. Our T surround is the surrounding temperature right there. So we can plug those in. Our epsilon value right here now is our emissivity, and we can see here our sigma here is our Stefan-Boltzmann constant. So we can plug into this equation here and then solve for our H sub R term, or our radiation heat transfer coefficient, in order to plug back in up here to our radiation resistance equations above. So next I want to take a look at contact resistance. Now we can see down here in this figure we have two different materials, material A and material B, that are in contact with each other here. So if we take a look right here at this section here, and let's blow this up, come over here to the right, and again we can see now material A and material B. Now a thing to note, for this contact resistance, these values are going to depend upon a couple different things. They're going to depend upon what material A is, what material B is, what their surface finishes are, how smooth they are, and then again some more information and values that we can see, which I'll show in a minute here, on tables 3.1 and 3.2 in your textbook here. So let's zoom in a little bit on this area here between these two different materials. So what do we have going on here? Well, we can see on the left side over here for material A, we have right at that surface there, we have temperature A. Then we can see over here we have temperature B on the edge of this surface over here. So temperature A and temperature B are going to become important, what those initial temperatures are in material A and material B. Now we can also see that we have heat flux going in our x direction here. So our x direction is defined going over this way like this for a 1D problem like this. So you have that heat flux there, and you can see we have heat flux from contact and heat flux over here from the gap in between them, and wherever air or fluid might be present in that gap there. Now this information comes into play over here in our governing equations that we see over here on the right. So we can see here we have our contact resistance per surface area, unit surface area there down here. So again, we don't have area coming into play out of this here, so we can see our equation here for dealing this for unit surface area now is TA minus TB. So the difference in the temperatures between material A and material B, or TA and TB, divided by our heat flux in the x direction right here. Now, our contact resistance here, if we're not looking at it per unit surface area here, this is our general equation now for contact resistance here. So you can see we can take this value that we have here and just divide by our area A sub C there. So again, that is the difference. We're talking about unit surface area here is that area. So all we've done is that same formula there that we see over here, but then divide all of this by our A sub C. So now on this slide here, we can see the table 3.1 that we were referring to in our textbook here. Now, this table here shows the thermal contact resistances for, in part A, we have the metallic interfaces under vacuum conditions, and in part B, we have the aluminum interface here with different fluids. So we can see here part A, vacuum interface, part B, with these different fluids listed over here. So one thing to note with this here is that the most reliable results for these thermal resistances are those that have been attained experimentally. So looking these up in one of these tables is one of the more accurate ways to do this, is looking back at people who have gone through the experiments, found out what these values are, and these seem to be the most reliable results. Now, the effect of loading on metallic interfaces we can see in part A here. Now, this presents an appropriate range of the thermal resistances under a vacuum condition. So you can see this is a range here. So again, a lot of these are obtained experimentally, so this is why we have that range in there. And then we can see over here the effect of interfacial fluid on the thermal resistance of an aluminum interface. We can see over here in part B. So we have these different fluids right here. We have air, helium, hydrogen, silicone oil, and glycerin right here, and their associated values. Pay attention up here to what our units are and the fact that this is times 10 to the 4th. Now in 3.2, what we have here in this table is we can see we have thermal resistances for different solid-solid interfaces here. So we can see if we have a silicone chip and lapped aluminum and air, or if we have aluminum with indium and foil, and so on and so forth. So they have a couple different of these configurations here for these solid-solid interfaces, and with that, the associated thermal resistance values here. Again, please pay attention to the units, and again, the fact that these are times 10 to the 4th right here. So now that we can see that contact resistance does come into play and is important to calculate here, this is where we really do need to pay attention to our problem statements. So does it tell us that there is negligible contact resistance, or do we need to consider that contact resistance between the different materials? So this is a big assumption and simplification to the solution of our problem there. So the fact that this says negligible contact resistance right here means we don't need to go through that process. We don't need to assign those values there. We're considering that to be negligible. And this is the case here if we're dealing with a composite wall problem here, that becomes important. So in this example here, we go over to the left, we have our given figure right here, and we can see within this figure right here, we have our composite wall here. We can see there's 3 different materials right here. There's material A, material B, and material C. So we've done a similar problem here, but with only one material. So now we're doing this as a composite of 3 different materials here, and you can see how that's going to change our governing equations and how we go about solving this problem here. So similar to our other problem with one material, we have an outside fluid over here, a hot fluid over here. We have our T infinity 1 and our H1 over here, and then on the right hand side of our wall we have over here a cold fluid with T infinity 4 and H4. Now again, pay attention to the indices. How does the problem label these indices, and how do you choose to label all of your variables with indices as well, and what does it mean? Make sure again on that setup page you clearly label, this is my value, this is my variable. The variable means this related to the problem here. So that's important to understand when you're actually creating your variables in these indices. So now let's look at the inside of this here. We have material A, material B, and material C that all make up this composite wall here. So we can see associated with each of these, we have some temperatures at the interfaces of all of these. So on the outside of material A, we have that surface right there, which we're calling TS1. So we're calling this position 1 when our X right here is equal to 0 at that outside surface at the interface with our hot fluid over here. So that's our TS1 there. Then we can see we go over, this is a thickness of LA. So the thickness or the length of material A in 1D is LA. We have a Ka value right there associated with material A as well. So then we get up into the interface between material A and material B, we have a temperature that we're going to call T2. Now T2 starts the beginning of this material B, which again has a thickness of L sub B, and it has a K value of K sub B here. That goes up here, and now we have the surface interface here with the third material, material C, which again has its own thickness, L sub C, and its value of K, K sub C here, and that's T3 is the interface between materials B and material C, where that temperature is. And last, we have our outside surface here of material C over here, which we're calling TS4. So that's where your 1, 2, 3, and 4 come in. All those different surfaces. So the first surface here, second surface, third surface, fourth surface. And that's going to be important now as we go on and draw out our thermal circuits. So again, just like we did in the other one, I really do like to take advantage of the fact that we have that diagram there. We've clearly labeled what each of those interfaces is and surfaces are between each of those, and use that to draw out our thermal circuits. So you can see I lined up right here. Here's your first, 2, 3, and 4, lined right up with those nodes on our thermal circuit right there. And then we can see on the outside over here where we have convection going on. So this is a fluid surface, fluid surface. So we have our two convection terms over there. So those are our two convection equations right there. So between our surrounding fluid temperature, T infinity 1, and our first surface temperature, material A, our TS1, we have convection going on right here, which is 1 over H1, there's our H1 right there, A. Then we have on the other side the same thing here, between our surrounding fluid over here, our cold fluid over here, and our outside surface TS4 over here, that temperature, that surface right there. Again, we have convection going on here, 1 over H4, there's our H4 right there, A right there. So those are our two convections going on our two outside surfaces there. Inside, we have conduction through each of those different materials. So I have material A, I have conduction going through here. There's my associated equation for conduction through material A. Then I have it for material B and material C as well. And you can see I've clearly labeled my temperatures each of these nodes. T infinity 1, TS1, T2, T3, TS4, and T infinity 4 over there. Those are clearly labeled. We can relate them back to the diagram. This makes your life easy. And also in our given statement, if we're solving this problem out, it'd be nice to write down what each one of those are in actual words as well for each of those variable names. So now that we can say our total thermal resistance here, or our total resistance here is the summation of all these thermal resistances there. So we can say, okay, well, there's a common 1 over A in all of these terms. I'm going to pull that out front right there. Then I have all of the remaining here, 1 over H1 plus LA over KA plus LB over KB plus LC over KC, all those lengths over those K values there, plus 1 over H4 is equal to, over here when I pull that A out, again, our prime total over that area there. So we have another way of expressing this down here. We have our overall heat transfer coefficient, our variable here, U. Now, this is a modified form of Newton's law of cooling that encompasses multiple resistances to heat transfer there. So that leads to these two equations, 3.17 and 3.19 in your textbook here, where you can see this R total here is 1 over this overall heat transfer coefficient, U, times our A value right there. And that is our R total right there. And we can relate that back to this above equation here. So let's look at a little bit more complicated case here. So we have a parallel composite wall, a series parallel composite wall. So this is interesting here. It's a little bit more complicated case, and this you can relate back to your courses in EE and electrical engineering for your thermal circuits right here that we're seeing. So the same type of thing of what do we do to add things in parallel and things in series right there. So this is going to all apply for this ME144 heat transfer course as well. So let's take a look at what we have in this diagram up top here. So we still have these two outside surface temperatures, T1 and T2. Let's just look at the actual materials here. We'll ignore the convection that we've seen in the previous problems now. We'll say, okay, we have a surface temperature here, we have a surface temperature here, but now we've got these 4 different materials right here, but you can see 2 of them right here on top of each other, whereas these 2 are on the other side over here. So this is series parallel composite wall. Well, how do we do that? Well, we can put our circuit down here as well into series and parallel. So we can see if we're going just right through this first material E right here, and we have conduction going on right here, we have our conduction equation right here, which is the thickness of this, which is LE, divided by our K value, which is KE, times our area there. So there's our equation right there as we're going through this one. But now you can see there's 2 materials here. We have material F and we have material G right here. Now they both have the same L value there. So LF and LG are equal to each other. But let's not worry about that yet. Let's just leave them in terms of their variable names right now. We just know they are equal to each other there. And now you can see we put these guys right here, where we have on top here our L sub f over kf times a over 2. So this is a over 2. So you're dividing that area now between the two of those. So that's what's important there as we're dealing with this part of the circuit. And down at the bottom here, you still have the L sub g, which is our L sub f still, divided by, now the difference is here, you have your K value for your thermal conductivity here of Kg, times that A over 2 there. And then again, now we're going back through this over here, just one material, H right here. So it's our general equation for conduction right there, LH over our thermal conductivity, KH there, times A there. Then we get to our temperature 2. Now, if we recall, go back to EE equations there. There's another way we could draw the same circuit out here. So we could draw it out in this manner here, where we take these two guys on the end here, and we say, okay, we're dividing those into two identical materials right there. So we do the same thing there, and it's just LE over the KE, and then this is A over 2, and it's the same thing on the top and bottom. And we do the same thing for material H over here, where we can draw it out in this circuit like this here. Now, thing to note here, these circuits are based on assumption of isothermal surfaces normal to the x direction, or adiabatic surfaces parallel to the x direction, provide approximations for our QX. Next, I want to take a look at a slightly more realistic and slightly more complicated problem here as we're dealing with a porous media. Now, one thing to note is as we move forward in this course and continue on to other courses where we don't have as many simplifications and assumptions to make the problems easier to solve, and we try to incorporate more realistic things, the complexity of these problems increases as well. So this is true with a porous media. So let's take a look at this porous media here. And one thing that we want to look at is there's two different types here. We either have saturated or unsaturated. Now in the saturated situation here, the media consists of a solid phase and a single fluid phase, whereas an unsaturated media consists of a solid, liquid, and gas phase. So let's take a look at a visual representation of a porous medium over here in this diagram. So we can see over here on the left in A, we have the medium and its properties right here. So we can go in, okay, there's our temperature T1, there's our temperature T2 over here. It's got some associated area here. We have all these properties right here. So this is for a porous media with all these different properties there. And what we want to do is simplify this down a little bit and come up with a representation that we're used to looking at. So that's what we do here in part B. And let's take a look at a series thermal resistance right here. So again, we take a look at this here and we have, okay, we have the properties associated with this first part, which we can see the thickness up here is given to us by this distance relationship here for 1 minus our epsilon right there times the length L. And L we see from our first diagram over here showing the medium itself and its properties is the total thickness of the entire medium right here. So this right here is in relationship to our value here for our epsilon value right there. So this thickness associated or simulated thickness right here, if we're trying to simplify this down into a form we're used to here to run our calculations, is given by that relationship. Then we can see over here on the second part of this material over here, the second material that we're calling over here, this distance right here is epsilon times that total length or total thickness L there. Each of these have its thermal conductivity value associated with it for each of those parts right there. We have this is our case of S and our case of F right there associated with each of those two types of materials right here. So we can see we also now have the surface temperature related to the surface at that material over here on that side, and over here T2 associated with that surface there. We come down here, next step, we line up all those guys right there to draw out our thermal circuit right there. So there's our T1 and our T2 right there. Then we have our conduction going through in our equation right there, which is our L value related to this length here, divided by our thermal conductivity for that material there times the area there. And the same thing over here, this, now our length right here is epsilon times L, which is our top value right there for thermal conductivity, over our thermal conductivity for that material, which is case of F, times A there. So this is our series thermal resistance right there in this diagram. Now in part C, let's take a look at the parallel resistance representation we have over here. So we can see for parallel, we have them in parallel with each other. You have T1, the material temperature for material 1 up here, T2 from a temperature of the material 2 down in the bottom right here. So now it's top and bottom rather than side to side. We're doing this in parallel representation for our resistance right there. So we can see now the total length is still L. So it's a little bit less complicated than dealing with this relationship here. So we have our L value there. Then we also see now, okay, there's our associated K sub S and our K sub F for the two different material properties right there. But now the difference is right here. This right here is going to be 1 minus our epsilon times this value for W there. And this is going to be E sub W right there, where now this width right here is W, and you can see that back over here in this initial diagram there. So that's the width right there. So it still relates it there. So is it any less complicated or not? No, but this is the parallel representation over here. So we do that out, we come down here, do our thermal circuit for a parallel right here. So there's our temperature 1, temperature 2, top material here. We have our L now on the bottom part right here for our area, and our K value right there, we plug this in right here, our K sub S times 1 minus epsilon times the area there. Then for the bottom material, it's L over K sub F times E A right there. For the bottom portion right there in front of our area there. So series and parallel representations for our thermal circuits. Now the effective thermal conductivity of a saturated medium depends on the solid or solids material, its porosity. There's our epsilon value right there that we saw before. That's porosity right there, and its morphology, as well as the interstitial fluid F right there. So we can go back up to that figure and take a look at that. We have our related governing equation here now, where we have our Q sub X is equal to our K effective times the area divided by that length L right there now, times our temperature difference between T1 and T2, which are our two surface temperatures on the outside of this porous medium. So this K effective that we see in this general equation 3.21 may be bracketed by describing the medium with a series of resistance analysis right here, which we can see right there. So there's our series resistance analysis right there in figure B, or we could do that parallel resistance analysis that we see over here in figure C. We can also estimate this value of our KEFF right here, K effective right here, utilizing the relationship shown in equation 3.25, which we have right here from our textbook. So let's take a look at an example problem. So right here we have example 3.5 from the text here. Now one thing to note about this problem here is this is all a word problem. There is no given diagram within this problem statement here. So one thing that we want to think about is it'd be very helpful if we take this information in the word problem and create our own diagram for this problem. Now this is something also that you should consider as we think about our group projects toward the end of the semester of what is more valuable to you. As you're doing a problem like this, would it be more helpful for you to have a diagram provided for the problem like this, or is it something that you want to challenge the other students in the class as for your problem when you create it to have to come up with their own diagram as well? So something to think about with this here, but either case, if you have a problem like this and you're not given an initial diagram, it is a very good idea and I highly encourage you to create one. So let's read through this problem statement here now. So we have a dormitory at a large university built 50 years ago, has exterior walls constructed with, and they give us our L value here, L sub S is 25 millimeters thick sheathing, and with a thermal conductivity of K sub S is equal to 0.1 watts per meter times Kelvin. So let's just pause here for a second. Let's think about what we have and what we need to do. So we know we really want to create our initial diagram. At the same time, we also want to create our setup page. And on our setup page, we want to list out all of these known values. So again, we want the variable name, the value, numerical value for it, the units associated with it, and how it physically relates to our problem. So all four of those things we want to come up with here. So we can see here, okay, we have an LS, a thickness, we have our units right here in millimeters, we have our value right here, and it tells us what it is and how it relates to our problem there. And it's nice because they also give us the variable names in this problem statement. Now they didn't have to do that. They could leave out the LS is equals. They could just say that we have exterior walls constructed of 25 millimeter thick sheathing, and not say LS equals, and not say thermal conductivity, but not say KS equals. So it is nice that they did give us those in this problem statement here. Now in a real realistic problem, not going to have any of that, and you might be out there physically measuring those dimensions and looking up these values from tables. So something to think about as we move forward there. But in this case here, they did give us the variable name with the indices, the numerical value, the units, and how it relates to problems. So we do want to write those down in an organized manner on our setup page. Now the next part here says to reduce heat losses in the winter, the university decides to encapsulate the entire dormitory by applying, they give us the values here, L sub I equal to 25 millimeter thick layer of extruded insulation, characterized, and they give us our K value here, by K sub I is equal to 0.029 watts per meter times Kelvin, to the exterior of the original sheathing. So now it makes sense if we go back up here why they say, okay, this was built 50 years ago. It's just not very well insulated. So as kind of a workaround to save energy costs or whatever it may be, they decided to add on this extra extruded layer of insulation around the whole outside and wrap the building. Now, this extruded insulation is in turn covered with an architectural glass. So they give us the thickness of that glass, L sub G, is 5 millimeters thick, and they give us our value here, our K value, thermal conductivity, K sub G is equal to 1.4 watts per meter times Kelvin. So now we can see we have the regular building, we know its thickness of the walls and our thermal conductivity. Then we have an extruded insulation with its known thickness and its K value here, our thermal conductivity. And then we have this architectural glass on the outside of that with its known thickness and K value as well. So we're starting to think about this and physically drawing this out. We're looking at one of these kind of composite materials right now, composite wall structures that we've seen before in a couple of the examples. Now we get to the point of the problem where they're asking us what to solve for. So they want us to determine the heat flux through the original and the retrofitted walls when, now they're going to give us our temperature information here, the interior and exterior air temperatures, they give us as T sub infinity I is equal to 22 degrees, and T sub infinity on the outside here, O, is equal to negative 20 degrees there. So we have our inside temperature and our outside temperature. We know it's in air right here. So now this should set off some red flags right here. We're dealing with convection. So we're dealing with convection there respectively. Now, what else do they tell us in this problem statement? Well, if we know we're dealing with convection, it'd be really nice if they gave us our convection transfer coefficients, which they do. So they tell us the inner and the outer convection heat transfer coefficients are H sub I is equal to 5 watts per meter squared times Kelvin, and our H sub O for the outside one now is equal to 25 watts per meter times Kelvin. So that's great. They gave us all that information, and as we've been reading through this, we've been highlighting things, looking at our variable names, our indices, our values, our units, and trying to come up with a drawing that relates back to some of the things we've seen in some of the other examples as we've been looking through and reading through our textbooks. So from here, the next step is going to create that setup page. Organize all of these variables in a nice, easy manner. Again, all four of those things. We want the variable name with the indices. We want the numerical value. We want our units, and we also want to physically state how it relates back to the physical parts of our problem here. So that's what we do here now. We come up with our setup page. So I take all that wordy information, I create a couple things. One, I write out all my givens. So here's all my givens right here. And two, I draw out my diagram over here. So this makes our life a lot easier as we're going through and solving the problem, figuring out our governing equations. Are we dealing with conduction? Are we dealing with convection? What are our thermal conductivities? What are our H values here for our convection heat transfer coefficients? All that information is a lot easier for us once we have it in a nice organized manner like we see here on our setup page, rather than going back through that entire problem statement and trying to read through that very wordy problem. So we see here, let's go through all of our givens. So we start. We can have this open, this paper right next to us as we're reading through that problem statement there, and we say, okay, 4 things I want. There's my variable name, L sub G. Here's my numerical value, 5. Here's my units, millimeters. And here's how it relates to my problem here. So I even went through and in red, did in a separate color here for us so we can clearly see what it relates to in our problem here, what our variable name is, which the problem was nice enough to give us those variable names. We didn't create them on our own. In other problems, we may need to create those ourselves, along with the indices. And we put that in there. Now, the other thing I noticed here is I've been doing this a lot of problems like this. You know, we're reading through our textbook. We've seen enough of these now, so far. We kind of have an idea of what our units should be. So we're looking at our units here for our K values, and we see, everything's in meters here, but our thicknesses, our L values here, are given to us in millimeters. So right away I decide, what, rather than worrying about doing my unit analysis later and conversion of units within problems, within the governing equations, let's just write them out here. Let's just do the switch all over, convert them all to meters right here on our given page. So I go right here from 5 millimeters is 0.005 meters. My L sub G, or my sheathing surface thickness here, is 25 millimeters, or 0.025 meters. My insulation thickness right here now, my L sub I, is 25 millimeters, or 0.025 meters right there. Now my K sub S, or my sheathing thermal conductivity, is 0.1 in units of watts per meters times Kelvin. Then I have my insulation thermal conductivity right there, my K sub I, which is 0.029 watts per meters times Kelvin. Then I have my glass thermal conductivity here, which is K sub G is equal to 1.4 watts per meters times Kelvin. And I have my interior air temperature, T sub infinity I, of 22 degrees Celsius. Take a note right here, we have Kelvin and Celsius. We could do the conversion now, but maybe we didn't catch it. Maybe we'll have to see what happens as we go through the problem. Then we see here we have our exterior air temperature, T sub infinity O, which is negative 20 degrees Celsius there. Then we have our inner convection heat transfer coefficient, our H sub I, as 5 in watts per meter squared times Kelvin. And we have our outer convection heat transfer coefficient, our H sub O, 25 watts per meter squared times Kelvin. Now, what do they ask us to solve for? Heat flux. So we'll keep that in the back of our mind, thinking about governing equations that we're going to utilize here. Now, the next thing that I want to do here is draw out a diagram. We didn't get one provided for us in the problem. So from that word problem there and everything we've read through and kind of wrapped our heads around, let's draw this out. So we have our building, our sheathing, insulation, and glass. So here we have our sheathing right here, L sub S. We know the value for this, the thickness is 25 millimeters. So we have our L sub S right there. Again, with these diagrams, I really don't like to include the numerical values. I'm just going to leave this in terms of the variables. We can reference back up top here to take a look at any of the actual values. So I'm going to leave it, keep it simple, keep it clean. Here, and we have our K sub S value right here for our sheathing. Then we have our insulation right here in the center, right here. So I have the width or thickness of the insulation, L sub I, and here's our K sub I there. Then we have our glass on the outside over here. We have our K sub G and our L sub G there. Then we have our indoor temperature, T sub I, with our associated H value right here, our H sub I value, or our inner convection heat transfer coefficient. Then I have my outer temperature over here, T sub infinity O, and our H sub O, or our outer convection heat transfer coefficient over here. So now I have a nice simple diagram, especially if I want to do it a thermal circuit. Now I've got a diagram that I can put on top and draw my thermal circuit a lot easier. It's going to make my life a lot easier to take the time now, create this setup page, create this diagram, write all my givens, and clearly know what I'm asked to solve for. Now the next step with this here is, what assumptions am I going to make? So from what we've read in the problem there and the information that they've given us and what they haven't given us, what can we assume? So we can make the assumption that we're dealing with a 1D conduction. It's going to be steady state, constant properties, and we're going to neglect any contact resistance. If they want us to deal with the contact resistance here, they would have given us some more information. So these are the 4 assumptions we're going to make going in to solve the problem. And it's important that we write out what we're assuming, because this does simplify down our solution to the problem here and make it slightly more unrealistic than if we were taking other things into account. So it's great to note those there. So with that, now we have our setup page, and this is going to be amazing for us to reference back to as we're solving the problem. We have a clear, organized spot with all of our variable names and values right there and units right there. We now have a diagram that we can use if we're drawing out a thermal circuit that we can use as a reference. So now let's take a look at this thermal resistance right here. Now the first thing I want to do is just the original wall. Before they wrapped it in insulation in the glass right here, we just had the sheathing right there and what it was when it was built 50 years ago according to the problem statement. So let's see how these compare with and without wrapping this with insulation in the glass. So we can see here, if we're looking at the thermal resistance and we draw out our thermal circuit here for just the sheathing, what we have right here is we have our inside temperature and our outside temperature, and we have conduction going through the sheathing in the center, but then we have convection on the outside, or the inside and the outside, all through the air right there. So we have convection, conduction, convection. So this is our total thermal resistance for original. So again, this is where our indices become very, very important. Original wall is what I'm calling when I'm just dealing with the sheathing right here. So my subscript, I'm saying comma original. So then I have values. I can go back to my first page. I can take a look at that setup page and clearly plug in. There's my H sub I right there, because I know for convection we have 1 over H sub I. For conduction, I have Ls over Ks, and for convection on the outside, I have 1 over HO there. I can plug all those values directly into this now here and say, okay, now I have my 1 over my value for HI is 5 in watts per meter squared times Kelvin. Plus right here I have my Ls, which is 0.025. I've converted to meters, put that in because meters and meters, times now divided by 0.1 in units of watts per meters times Kelvin right there. Then we have 1 over my HO value right here, which is 25 in watts per meter squared times Kelvin there. Go ahead, do plug these into a calculator, Excel, whatever you want, do them by hand. You have 1 over 5 is 0.2, you have 0.025 over 0.1 is 0.25, and we have 1 over 25 is 0.04 right there. Paying attention to all of our units as we do this. Okay, that meter's there, the meter's there, okay, that's meters squared. If everything does check out, we're okay. So now we're all in meters squared times Kelvin over watts when we do out our unit analysis, which we want to do. It's a great way to double check that everything is correct and we have the units correct and we plugged in the right equations and the right values. So from that there, we can add those together. We end up with our total thermal energy for the original, if we're just dealing with the sheathing right there and we haven't wrapped in insulation of the glass yet, of 0.49 meters squared times Kelvin divided by watts. Now this is where it's important to have that find section. What are they asking us to solve for? With a lot of these problems, we have these multiple steps along the way. Well, that's only a part way along our solution right here. They want us to find our heat flux right here. So recall our general equation for heat flux right here. Well, our heat flux Q double prime right here is equal to our T infinity I minus T infinity O, or the inside fluid temperature and the outside fluid temperature right there, divided by our total resistance, in this case here for the original wall. We're just dealing with the sheathing right here. Well, these values were given to us in Celsius. Now, I left this in Celsius. We should convert to Kelvin. If you're doing a difference between them, though, you can get away without the conversion. So don't let this fool you when you're doing other problems. And I still would recommend, even though I left this in Celsius right here because I knew it was the difference between, and the difference between 2 Celsius temperatures, the difference between 2 Kelvin temperatures is going to be the same, go ahead and convert everything to Kelvin. Look at your units. Don't make that mistake where you think you can use it because it's a difference, but you really can't because you're plugging in something else. Be careful with that. Be cautious with that from there as you're moving forward. So it's a little side note there. So we do our temperature difference right there between the inside and outside air temperatures right there, divided by our thermal resistance total, which we just calculated above. Again, for our original wall, just the sheathing, we do that out there. We can do our math. What we end up with when we check this out here is our Q prime, double prime, or our heat flux is equal to 85.7 watts per meter squared. Again, pay attention to those temperature units when you're doing this out to come up with the correct units at the end. That's a great double check. So we looked at the original wall and we saw what our heat flux was. Now we want to know, with this insulation that they're adding on to this and with the glass layer that they're adding on to this, how does that affect our heat flux? So the first thing we need to do is first, how does that affect our total thermal resistance right here? And then from that, we can plug into our equation for heat flux, just as we did for the original wall, and see how it affects our heat flux at the end now. So we go here. Here's our retrofitted wall. So I'm calling this retrofitted and original. So my subscripts are RET for retrofitted there. So this is something you choose to do on your own. It wasn't given the problem statement. So make sure as you're choosing those, it's clearly labeled what RET is. It's very clear so somebody else following through your work can understand, or if as you get further along, you need to plug into future equations, you understand what it is. So this is one where I would suggest you go back to the original diagram that you just drew, draw out your circuit directly underneath it, line up those nodes with the temperature spots on it. But what we can see is we have the two air temperatures inside and outside. So we have convection on the inside and the outside of those two surfaces right there. And then we have conduction through the 3 layers. You have your sheathing, your insulation, and your glass. SIG, sheathing, insulation, glass right there. So now we have associated convection relationship here, 1 over HI for the inside convection, 1 over HO for the outside convection there. And then for the first conduction, we have LS, the thickness of the sheathing, divided by its thermal conductivity, KS there. Then we have, through our insulation, Li, the thickness of the insulation divided by the thermal conductivity of the insulation. Then we have our L sub G, or our glass layer here, so we have L sub G, the thickness of that glass layer, divided by our thermal conductivity of that glass layer there. So then we can go ahead and say that our total thermal resistance of retrofitted, there's again the RET right there, is equal to the sum of all of these internal resistances right there from each individual part right there. So 1 over HI plus LS over KS plus LI over KI plus LG over KG plus 1 over HO. Now that I have the general equation, I can go back to that lovely setup page that we've created and simply plug in our values. We do that there, we end up with 1 over 5, 0.025 over 0.1, 0.025 over 0.029, 0.005 over 1.4, and 1 over 25. Now pay attention to your units, do out your unit analysis, make sure everything's in meters and not in millimeters. We were lucky enough that we thought about that in advance and converted them to meters rather than millimeters to begin with. So it is a straightforward plug. We don't have to do any side conversions and get more messy over here, put in a conversion factor into our equation. It's nice and neat, keeps things simplified. We do that, do out our math there. Our thermal resistance total for our retrofitted wall right here is 0.2 plus 0.25 plus 0.862 plus 0.00357 plus 0.04 in units of meters squared Kelvin per watt over there. Do out our math, this ends up being 1.355 in those same units. Now again, we want heat flux. So we plug this into this relationship between our temperature difference between our two fluids on the inside and the outside temperatures right there, divided by that total thermal resistance for the retrofitted wall. So now it's the same equation as before there, but now we're dividing by this new value here for this thermal resistance that we've now calculated for our retrofitted wall with our insulation and glass wrapped around it. So now from that there, we can find our new heat flux value of 31 in units of watts per meter squared. Again, double check, do your unit analysis out, make sure that comes out correct, and go from there to get your heat flux now for the retrofitted wall.